So in this video, we're addressing solving the differential equations that are in the form of proportional, inversely proportional, jointly proportional. It's really nothing different than what we've been working with. Just the exception here is that you have to come up with, from the form of a word problem, the equations themselves. All right. So what I'm going to do is I'm just going to take you through something that's similar to the form of a problem that we've worked with previously, and then from there we'll delve into the world of the word problems. All right. So when we're separating variables, the first thing we want to do is make sure that those, I mean, it's going to sound simplistic to say this, those variables are separated. The k is a constant of proportionality. Well, anytime, a constant of whatever, it doesn't matter. It's constant. It can go anywhere. So I'm going to leave the dp on the left, and I'm going to leave k over 10 minus t dt on the right. All right, so I'm leaving the k over 10 minus t on the right, but then I'm bringing over the dt as we've been doing. All right, so understood one, I'm going to integrate both sides. So go with blue for those keeping score at home. Poor quality integration symbol. So I'm going to integrate the 1, which is going to become a p. And on the right-hand side, well, we have a constant that can be factored out. Now, the bottom part, when you're dealing with something that's in the form of a natural log, it can be a little iffy. What I recommend is it's a little slight adjustment, and it might make all the difference. I don't know. That negative t tends to throw people for a loop. So what you can do is actually factor it out. All right. So I'm going to write that as k over negative t minus 10 dt. And then I'm going to factor, let me get a little highlighter action going on over here. I'm going to factor that negative and the k out. All right, so negative k, because k divided by negative 1 is still negative k. It's not a constant of integration, so the k wouldn't absorb the negative 1. It's a different type of constant, like coefficient of static friction or something, like a known quantity, right? Not the unknown type of constant like the constant of integration would be, right? So negative k times the integral of 1 over t minus 10. Oh, I don't know why that little minus sign bothered me, but it did. Then I can integrate, and I'll be left with p equals negative k times the natural log of t minus 10 plus c. All right? And that's the solution to the differential equation because I don't have an initial condition. And so at that point, I'd have to just leave it. Now, if you had left it with the 10 minus t, you could still work with it, except you'd have to correct for the fact that when you take the derivative of the natural log of 10 minus t, it would actually be negative 1 over 10 minus t. And you actually want positive 1 over 10 minus t. So you'd have to correct for that with a negative sign. Not terrible, but I think it's a little bit more procedural to do it this way. Up to you, but if you see it the one way, then go for it. If not, then this way might be a little bit easier. All right. Number 2, solve the differential equation that models the verbal statement. All right. Proportional, absent of any other words, means directly. All right, so if it said inversely proportional, then it's obvious, or jointly, same deal. But if it just says proportional, then it's directly proportional. The rate of change of p with respect to t. All right, so that's the same as saying, so I'll underline that in blue. That part is dp dt is proportional to 25 minus t. All right, so proportional is in the form of y equals kx. So if you just refer to the top of the page, you see the function, or f of x equals kx. Either way, the constant k multiplied by whatever it is proportional to. And so I'm going to throw a little, I'm going to throw a little Easter egg in this video. I'm going to make a side example where we'll tackle one where it's inversely proportional, even though number one is along those lines. There's no verbiage that actually addresses that, or verbiage, I don't know, language. Oh, there's another Easter egg. Right, so the first person, so two Easter eggs in this video. So the first person who sends me a message telling me the correct pronunciation, is it verbiage or is it verbiage, gets a bonus point. And the first person with the typo that I should include an example on this page of rate of change of p with respect to t that is inversely proportional to 25 minus t. So same problem, just I want another one that has inversely proportional, another opportunity for a typo bonus point. All right, so the t's are on the right, so dp would be equal to k times 25 minus t, poor quality t, still poor quality t, but now I feel obligated to live with it, dt. All right, I'm going to integrate both sides, understood 1 in front of the dp. So p on the left, I can pull out the k, 25 minus t dt. All right, I apologize, my wife is a loud phone talker. So if you hear her in the background, I really have no control. I told her I'd be making a video, but she's passionate about gossiping. So here we are. So p would be equal to k times, so I'm going to integrate 25 t minus 1/2 t squared plus c. And at this point you can clean it up if you want, but you don't have to. I leave it up to you, but it's actually really distracting. I leave it up to you, but and so you can leave it in this form. I could distribute the k. But once you multiply the k times the c, the c is actually going to absorb the k. All right, so it's just going to be a plus c at the end. All right, so this is what would have happened if you had distributed the k first and then integrated from there. All right, either way is fine. I like this way, but you know, it's up to you. Joint proportionality, rate of change of y with respect to x, so dy dx, varies jointly as, so we have still a multiplier of k as k and L minus y. All right, so L minus y. So I'm going to pull the L minus y to the other side of the equation. I'm going to leave the kx on the right hand side. So 1 over L minus y dy is equal to kx dx. All right. I'm also going to use that little nifty trick I used in example A, and that is to pull out that negative sign in front. And so I cut myself off there, but really I just want to emphasize that if the variable, if you recognize something as a natural log derivative, if the variable is negative, that's when this technique would apply. All right, so I'm going to factor out that -1, and that's going to give me a 1 over y minus L dy, because L, you know, I glossed over this point, but L is, All right, this is probably the dumbest thing I'll ever say to anyone on a video. L comes after K in the alphabet. Let that sink in for a second. The reason why that's important is because if we're establishing K as a constant, then the letters in the alphabet that immediately follow that would also be constants. Just like we establish X as a variable, the letters that immediately follow it in the alphabet are also variables. All right, so L would also be considered as a variable. So we have K in this case and L. All right, the reason why I didn't put K in the word problem is because I knew that we would be using K in the setup of the joint variation. All right, so on the right hand side, I'm going to have the kx dx. All right, I'm going to integrate. I'm going to pull out any constant multiples, so negative antiderivative 1 over y minus L dy equals k antiderivative x dx. So negative ln y minus L equals kx plus c. Got a little bit of extra work to do here because we have to solve for y. And so I'm going to multiply both sides by negative 1. So ln y minus L is going to be equal to negative kx plus c. All right, so notice how the k does not absorb the negative sign. We're negating k, but c does absorb the negative sign. So that goes back to what I was saying in, I believe, the first example. All right. So then we know, additional step here, some of you can do it in your head, and that's fine, that these are equivalent. So I'm going to swing around the e and convert into exponential form. So the absolute y minus L is equal to e to the negative case x plus c. So we're on page 12 in the packet. So by now, in theory, the next step should not be black magic. We're going right to c e to the negative kx. All right, and that's because we can split up that plus sign to make it e to the negative kx times e to the c. All right, and e to the c is a constant to a constant, which becomes a constant. All right, so we still have the y minus L. Now that y minus L in the absolute value is really plus or minus y minus L. The plus or minus will get absorbed by the c. So y minus L would be equal to c e to the negative kx, making, at long last, y equal c e to the negative kx plus L. All right, so that was a lengthy one, but not too terrible. All right, so as promised, I'm going to make an example. I believe this would be C. Yeah. So rate of change of P with respect to T is inversely proportional to 25 minus T. All right, so C with respect to T is inversely proportional to 25 minus T. All right. So the first part, just like we've been doing, dp dt, pardon the abbreviations, inversely proportional, so k over, let me stay with my color coding system here. It was working so far, why give up on it? Inversely proportional, k over 25 minus t. Well, it was working for me, so, there's that part of it. So, clean it up, a little housekeeping. dp is equal to, I want the t's on the right, the p's on the left. There are no p's. So, k over 25 minus t dt. Constants come out. All right, so that little nifty trick. So I have a negative in front of the t. So I'm going to factor out a -1 while I integrate. So left-hand side will become p. I'm going to pull out a -k. It'll be the integral of 1 over t minus 25 dt, which ends up being p is equal to -k ln of t minus 25. The whole shebingity bangity boomity bobbity bibbity plus c. All right, because either way, if I put parentheses around the ln t minus 25 plus c, or if I don't, one way or the other, it's just going to end up simplifying to this expression. All right, so that gives you hopefully a nice little tutorial on the myriad of different ways in which we could address proportionality, because some of the word problems that follow, actually all of them, are going to incorporate these concepts in some way. All right, and there it is.